Hey Warriors, this is the description of the lab for radiometric dating. Okay, so what I have here is a graph, kind of an empty data table ready to go. It's just going to graph for me. I've got a flat area here, and I've got some M&Ms. We can do this with M&Ms, Skittles, anything that really has two sides so that we can tell a top from a bottom. And so all I'm going to do to start with is I'm going to see how many M&Ms I happen to have in that cup, and we're going to go from there. Okay, Warriors, so I counted those M&Ms. I have 75 M&Ms, so that's going to go, I'm going to record that right there. And then what I'm going to do, radioactive decay is like trying to hold on to a handful of ping pong balls, right? If I tried to hold on to a handful of ping pong balls, I'd have to squeeze them just right. I'd have to get them arranged just right in order to hold them in my hands. If I had too much pressure or not the right number, I'd lose them and they'd go shooting out, right? And so that's kind of like a radioactive element and radioactive decay. You've got those nuclear forces trying to squeeze the nucleus together, and as it does that, it might shoot out a proton or shoot out a neutron, and that's called radioactive decay. And just like in those ping pong balls, I'd be able to hold on to that. I'd be stable once I got it just right. That's what a stable atom then will do. Once it shoots out the right number and it has the right amount of force and the right number of protons and neutrons, it becomes stable. So we're going to represent that here with shaking of this cup. I'm going to pick a random number because every radioactive element has a different half-life. So I'm going to pick a random number between 1 and 10, and I'm going to shake the cup that many times. Once I shake the cup, I'm going to kind of dump those out and lay them flat. And if they land M up, I'm going to count those as still radioactive, and they're going to go back in the cup. And if they land M down, I'm going to count those out and sort them to the side as a stable atom. Okay, so I've sorted them out, and now I can count these. So that's 10, 20, 30, and there's 7 right there in that pile. So that number 37 is going to go right here in this red box. And now what happens is it will start to graph that for me in the spreadsheet. And so I'm going to finish out, I'm just going to keep moving these ones that have decayed out of my radioactive sample. And so I'm going to push those over to the side, and I'm going to keep going until there's no M&Ms left in the cup. So now you can see what my graph looks like. And so you can kind of see it's kind of below this line. We've got this green line that represents our control, which represents approximately half of all M&Ms decaying at each point, which now we need that definition of half-life. A half-life is how long, the amount of time it takes for half of the atoms to decay. So what you should see here is that in my example, about half of those M&Ms flipped over every time. So now what I need you to do is go look at the other examples of student data. So lots of students over time have done this. We've collected their data, and we want you to see if my data is reliable.